All right, everybody, welcome to meeting number 4 of our data science study group with Python. And I always forget the name of our book. I'm great like that. Practical Statistics for Data Scientists. We're doing this book using the Python examples. This week, we're doing Exploring the Data Distribution chapter. And so essentially in this piece, so what we're doing, we're looking at data, looking at the distribution, and then we're going to look at different ways that make sense to go ahead and plot that data, break it down, and show what we're seeing. I know that's probably implied in the explore the data distribution piece of it, but there we go for that deal. So I think everybody's probably just a little bit familiar with things like box plots and histograms, frequency tables, and stuff like that. But it's probably going to be a good deal to go over it and take a look at it. So our key terms, like I said, here we see are is box plot, which is a plot. Which is just a quick way to go ahead and visualize the distribution of data. You're going to have your X and Y axis, and you're going to see where things are done across. A frequency table, which is just a tally of how many times things happen and fall in a certain value. So once, twice, 3 times, whatever else. A histogram looks a lot like a bar chart. But instead of representing X, Y, distribution like in a bar chart wise, that is also based on frequency and what's going on there. So hopefully they'll give us some examples we can look at here pretty quick. So percentiles and box plots. So we talked about before in estimates of variability and stuff, the estimates based on percentiles. So, we have our quartiles, between the 25th and the 50th percentile, and 50th and the 75th, and so forth and so on. So these are especially valuable when we're summarizing tails, the outer ranges of the distributions, and then popular culture has coined the term 1%ers and stuff. To refer to, of course, people that, all the way at the top 99th percentile for wealth and things of that nature. What we see here, again, as a little code example, where we're looking at quantiles for murder rates in states, which, if you want to feel good about where you live or something of that nature, maybe you don't want to look up your state. We'll see how that kind of deal works. And then we see there that and pandas and for the data frame, they're doing the same thing. So kind of move on. So as you can see there, percentiles of murder rates by state. This is broken down. The median there is 4 murders per 100,000 people. Oh, there's quite a bit of variability. The 5th percentile is only 1.6, and the 95th percentile is 6.51. I feel like that's probably, it seems kind of like that's data maybe from kind of like our last chapters and stuff that's mixed in all of a sudden. Doesn't feel like there's a clear delineation between the stuff that we were looking at there and now moving on to box plots and stuff. But again, box plots, they were introduced by Tucky, who of course is, one of the fathers of data science and the things that they're doing. They're based on percentiles that give a quick way to visualize the distribution of data. And then they show box plots. So it looks like we can do a short or easy box plot in R or pandas. And here we are, right there is a box plot. I think, honestly, this is probably the first time I've ever seen a box plot. Nathan, do you have any kind of feedback on that, or is this something that you run into on a regular basis or see in your work?
Yes, I do. You know, before I started working in data science, I never saw a box plot, and now it's one of my favorite kind of visualizations, actually. So it is something that it takes a little getting used to figure out what you're looking at, but once you get used to reading it, it can be really valuable. And especially where I find box plots are useful is if you had a couple of different categories, like if you had Midwest population versus Northeast or something like that, and you could put two box plots next to each other, and then it's easy to see how compare two distributions to each other. But the thing to remember when you're looking at a box plot is the box part represents half the data. So 50% of the data falls between the bottom of the box and the top of the box, and then that thick line in the middle is the median. So that's the 25th percentile to the 75th percentile. So when we talk about the interquartile range, that's what that box is showing you. So half the data falls inside that box. And then the whiskers on either edge show you kind of the normal expected range where the rest of the data would go. So you can see on this picture, the bottom whisker doesn't extend very far below. That's because you can have a population less than 0. So the bottom of that bottom whisker represents the population of the very smallest state. And on the top side, you can see that there's a top whisker there, and then there's a few outliers. So New York, California, whoever our biggest states are outliers, and they're represented as individual dots. And for most of the box plots that I'm used to looking at, the longest that they'll let that whisker go before switching over to plotting individual dots is 1.5 times the interquartile range. So, you know, the box represents the middle 50% of the data. And then if you took that box and shifted it up, now we're looking at from the median up to that top whisker, that represents the top 50% of your data. And then conversely on the bottom side, the median down to the bottom whisker represents the bottom 50% of your data. But that top whisker, they're never going to let it go more than 1.5 times the interquartile range. So if you've got a few outliers like this, they're not going to extend that whisker clear up to 35 million, 40 million. They're going to cut it off at 1.5 times the interquartile range. So that's giving you a good visual of kind of where almost all of your data is going to lie from the bottom whisker to the top whisker, and then there can be a few outliers beyond that.
Okay, that's great. It's very succinct breakdown there. So yeah, their little thing is, you know, the box plot, you can see that the median state population is here, correct? You know, where we're looking at the middle. It's about 5 million, and then, you know, basically, so half the states fall less than that. You know, the other half are a bit more than that, and then again, you said you have your outliers here, all the way that run out there. So that's new. Learn something new today. I've never seen that.
So if you had like a bell shape, I mean, a lot of times when I see a box plot, I kind of turn my head on side and think about what this would look like if it was a histogram. So if this was a perfectly symmetrical bell-shaped curve, then you would have the box plot would be symmetrical to your bottom whisker, and your top whisker would both be the same distance away from the median. And you'd have, you know, the quartiles would be dividing the picture just evenly. But since we've got this is asymmetrical, right? It's not distributed evenly below the median compared to above the median. We can just tell that by looking at the box plot that this one tends to have some outliers on the upper end.
Okay. Yeah, no, that makes a lot of sense now after we're looking at it. Okay. And so for you and your work and your stuff, what is this most used for to represent?
Well, so a lot of times I'm using this when I'm trying to get a quick sense of the distribution of my variables, when I'm going to fit them for a model. And so if I get a box plot and it looks kind of like this, except for the bottom half is totally squashed down and then the top half goes off forever, then I know, oh, this variable probably needs to be transformed before I can use it in a linear model because it's highly skewed, you know, in one direction or the other. The other way I would use it is like if I'm trying to predict a yes or a no, is somebody going to buy a product, or is some event going to happen? I would take a continuous variable and do a box plot of the yeses and a box plot of the nos next to each other. And if the yeses and the nos box plot look a lot alike, then this variable probably isn't going to be very helpful in predicting the target I'm trying to predict. But if I see a difference between the yes box plot and the no box plot, the medians don't align very much, or especially if the interquartile ranges don't align, then I know, oh wow, this is going to be a really good predictor. If I know if it's above this certain level, then it's probably a yes. If it's below this certain level, it's probably a no. So that's one place where putting two box plots side by side can be really helpful as you're trying to figure out your feature selection of which features are going to be good useful ones for your model.
Okay, that's a great example. Let's see what we have here next going on. Let's see there. Yeah, so they go on to explain the box plot, and as you said, top and bottom of the box are the 75th and 25th percentiles. That's our interquartile range, correct? That's what the
IQR is, yes.
That's what that's called. And like you said, the actual top whisker there is not going to extend beyond, we have it right here, the 1.5 times of the IQR.
Right.
So we saw that, we got that broken down. That's a pretty good deal. So any data outside the whiskers, they're outliers. So we're going to go there from there. That's a pretty intuitive way to figure out, okay, look, these are things that are different. So the next thing we're talking about here, is frequency tables and histograms, and we'll just read the variable here. A frequency table of a variable divides up the variable range into equally spaced segments and tells us how many values fall within each segment. So we have a table coming up, some good code examples and all of that, but we see here, what's a bit?
I've never seen that cut before, but I like that. I've done something like that, but in a much more complicated way.
Yeah. There's another pandas function called qcut that will do the same type of thing, but on quantiles instead of on bin sizes of integers like this.
Okay, nice.
So let's see here. We are getting a frequency table of some kind of population count, binned population counts. Getting counts for that. So we're getting frequency, bin range, bin number. And that goes on here again. So these are, looks like, I'm understanding it, the bin sizes are what we're looking at, how the frequency of things that we're getting there. So like text, the 22 to 26 million, we're only getting one in Texas, and then the 33 to 37, we're getting one in California. Go back and take a look. That our box plot there, where our lowest wasn't 0, but our lowest it was 500,000, and then we, the bottom half of that quartile or whatever was 4 million, and that captures, like I said, the majority of the states here is 24. So that makes pretty good sense. And then we go from there and move on. So this is how they're showing a frequency table. I think that all makes pretty good sense. This, I guess I haven't seen this before. So the bins, they say them being broken down into bins. I'm guessing that's saying, okay, this is this box is this size, this box is this size, sorry, this bin is this size, this bin is this size, and then we'll break it down and see the frequency of how we fill these bins.
Right. So they decided they wanted 10 bins. And so the bin size is determined by looking at the population of California and then the population of Wyoming. So you got that range of, 97 million or whatever. And then you're going to divide that into 10 equal sized units. And so each bin is the difference between California and Wyoming divided by 10. And then you've got those 10 equal size bins that you can fit the data into.
Works pretty good. Let's see what's next here. So yeah, again, there's your lowest bins, and then your contrast, your highest bins. So what does it say here? The 2 bins immediately below California are empty until you reach Texas. It's important to include the empty bins. The fact that there are no values in those bins is useful information. It's statistically significant or whatever that, hey, we've got some empty spaces here. This is, you know, and also provides probably a pretty good illustration of the gaps in between.
Yeah, so when you're using different plotting software, sometimes if you don't tell it you're trying to do a histogram type of a plot, that space in between will collapse and you won't notice that it's there. And so that's why it's nice with Python to make that frequency table that will show you, yeah, there's space in between here. You don't want to forget that it's there.
Okay. And I like here it says, you know, it's useful to experiment with different bin sizes because you can get too granular or it doesn't help you, or you can make them too large or it doesn't help you. Same type of thing. So it says both frequency tables and percentiles summarize the data by creating bins. In general, quartiles and deciles will have the same count in each bin, equal count bins, but the bin size will be different. The frequency table, by contrast, will have different counts in the bins, equal size bins, but the bin sizes will be the same. So makes sense. A histogram is a way to visualize a frequency table with bins on the x-axis and the data count on the y-axis. So it says we're going to get an example here coming up. We are doing states again. Looks like we're doing population in the states. And we are breaking that down into bins again. So here we are again. Bars are continuous, no empty spaces shows between bars unless there's an empty bin. So again, our histogram here is, you know, histogram of state populations is showing us in the bar chart form versus, you know, kind of like the box chart or whatever else, our state populations and where they fall into these bins, which is, it's not terribly exciting, but it's it's again easy to see, right? We can look at this and be like, all right, okay, you know, there's only so much happening over here where these are very, very large, but as we come back, you know, to the population size, it gets smaller, where we see that happen a lot more often. And, you know, we have our 24 states that fall into that one bin there.
Your histograms are a good way to find outliers. You know, if you're first getting a data set that you don't know, you know, how clean is it, what's in there. If you plot a histogram, then that outlier way out on the edge, kind of like California, sometimes it's even much farther out on the edge than that, will really jump out to you. And so that's one useful thing to understand with the histogram. And then some models are going to assume that we have that symmetrical bell-shaped curve of a normal distribution. And if you have fed this data in assuming that it was a normal distribution, your result wouldn't be very good because this is clearly not that bell-shaped symmetrical curve. It's definitely skewed. And so you could just spot that instantly by looking either at the box plot or at the histogram. They'll both tell you right away that if you're going to use this, you might need to transform the data in some way.
Gotcha. So let's see here. I have, one too many. So okay, we've gone through. We've looked at the percentiles. We looked at box plots, frequency tables, and histograms, and seen how they're all useful in their way. And like you said, especially as far as displaying outliers and doing things of that nature. And they'll all have their little special ways of blocking that out. Density plots and estimates. So related to a histogram is a density plot. It shows the distribution of data values as a continuous line. A density plot can be thought of as a smooth histogram. I like that. Like, so it's, we see it that way. Although it's typically computed directly from the data through a kernel density estimate. So again, we have our little code examples, which we haven't done. I swear one of these chapters we'll pull the code out and do some code examples so we can make that a thing. Again, we can see we're looking at murder rates because those are exciting, I guess. We have the plot is going to be a histogram, and we're going to do it in as a density plot as we do that. So the key distinction from the histogram plotted is the scale of the y-axis. A density plot, it corresponds to plotting the histogram as a proportion rather than counts. So that's where we get our smooth line and the things of that nature. Note the total area under the density curve is 1. Instead of counts and bins, you calculate areas under the curve between any 2 points on the x-axis. So let's check this out. So here is our histogram, but with like a density plot overlaid on top of it. Which, I don't know, that's kind of I don't know. It's hard to tell. Like I'm trying to personal preference this. Like what I want to see if I was looking at this particular deal, and I kind of feel like the histogram in that is clearer for me, but you might have a little more insight in there, Nathan, as far as like where you would use something like a density plot.
I agree with you that I normally just stop at the histogram and don't do the density plot. Because they're basically telling the same story, right? The thing that a density plot reminds me is that often I have only a sample of data, that there's probably many, many more examples than what I've already measured out there. And so the histogram is giving you an actual count of the data that you really have. The density plot is saying if you could, continue to gather data, and kind of goes back to that bin size, right? If you had enough data that you could make your bins infinitely skinny, you'd end up with this density plot because it would eventually, those rectangles get narrower and narrower, and then you kind of get this smooth curve. And so that's what it reminds me when I see the density plot, is that there's probably a lot more data out there, but we just don't have it. But if we did, this is what we think it would look like.
Gotcha.
If you go back one, there is some Python syntax that we could talk through, because I find matplotlib not the easiest to work with, but it just takes practice, right? So what you've got there in that first statement is the plot function. There is returning the axis, and the axis is where your picture lives. And so the first line that ends on the bins equal range 1 through 12, that's just making the histogram by itself. And then the next line there is saying, okay, now give me the density plot, but it's passing in the same axis as a parameter to that plot function. And so that's why you've got two different plots on the same axis, the histogram and then the density plot. And then finally, we're also taking that same AX axis variable again, and we're modifying it with the set X label function there. So as you start to work through the matplotlib code, you'll see sometimes there's a figure and then there's an axis, and the axis is just what you'd think. It's the X and the Y axis that holds your picture. And sometimes it gets passed around and recycled as you plot the same thing on the same axis, or multiple things on the same axis. That's the way that matplotlib is keeping track of where that picture should live. There's also, you can set the figure size and the y-axis labels, all different kinds of things you can modify with the figure and the axis things that get returned from this plot call.
Okay. Yeah, that makes sense. That way, you're able to do the double plots and take a look at it.
Right.
So there we are looking at that. So density estimation methods and pandas and scikit-learn offer good implementations. For many data science problems, there's no need to worry about the various types of density estimate. It suffices to use just basis functions, what it says. So our key ideas out of this exploring the data distribution piece, a frequency histogram plots frequency counts on the y-axis and variable values on the x-axis. It gives a sense of the distribution of the data at a glance. We looked at that. That works pretty good. Frequency table is a tabular version of the frequency counts found in the histogram. The box plot, which is brand new to me today and which we're learning a little bit about, with the top and bottom of the box at the 75th and 25th percentiles respectively, gives a quick sense of the distribution of data. Is often used in side-by-side comparisons to compare distributions, which is what you were talking about, looking at yeses and nos and seeing if that's going to be a good feature to work with. And then, of course, again, we looked at a density plot, which is a smooth version of the histogram, and it requires a function to estimate a plot based on the data. We have some further reading if you want to check this stuff out. We have a professor providing step-by-step guides to creating box plots, density estimation, some more R stuff, and then Matthew Conlin published an interactive presentation that demonstrates the effect of choosing different kernels and bandwidths on kernel density estimates, which I'm not sure what that is right now at this moment. So that might be something I might have to go check out. What are kernel and bandwidth density estimates? Work on that.
Yeah. I mean, I would say that's a pretty low priority concept in general, that almost always a histogram or a box plot is going to tell you what you're going to need. So the density plot is nice to have, nice to know, but that's probably not a need to know.
Well, fair enough. So yeah, in this, I think it's safe to say, at least for myself, the percentiles and stuff, we've heard that a number of times now, and that makes sense. It breaks down. Learned new information with regards to the box plot. So that was neat. I've never seen it, and so it's cool to learn. And it actually said it as once you see what the picture is, it's a really quick breakdown of what's there and what the outliers are. Frequency tables and histograms, I feel are probably pretty familiar to most people, and hopefully so it didn't require a lot of elaboration on my part, because I didn't give hardly any. It works that way. And then, as you said, the density plots and estimates are things that do exist. There is a lot of knowledge out there about them, but seem to be kind of like on the low importance end of the scale for things of that nature.
Good summary.
I try. So that's what we have for this week. I don't think if anybody wants to keep going, but I think the one heading per deal is working out pretty good. None of this stuff seems to be too terribly heavy. When next week, God willing, and a creek don't rise, we'll go ahead and get ahead of this and do some of these code examples in the Colab or in a Jupyter notebook. So that we are doing a little bit more with the code and doing a little bit more with that kind of stuff, just to let people see how that looks and maybe some of the stuff that we can build with it. I feel kind of like at this particular point, I'm falling down on that end of the scale. So. But let's see. So today is the 23rd. That means our next meeting will be on the 30th. On the 30th, we will be going over exploring binary and categorical data. So everybody get on the edge of your seat for that deal. We're rocking along, doing all of that. Any questions, any feedback for today? Do you know anything we felt like we needed to look at better or do different?
It's a good session.
Yeah, I think it's still just kind of building the fundamentals before we start to get into the meat.
Yeah.
Absolutely. All right.
Foundation.
Well, gentlemen, thank you very much. And I definitely appreciate it. And we'll see y'all next week.
Have a good one.